Welcome back to my channel Easy and Inspire. In last session we have seen first type of register, that is nothing but serial input and serial output. In today's session I am going to discuss about serial input and parallel output register, that is nothing but SIPO register. Please pay attention. So this is the block diagram of SIPO register. So serial input. So the input must be serial. See here, data input and clock pulse. So I am not at all discussing about clock pulse. So the input must be serial to this register and output is taken parallelly from each and every register flip-flop. From each and every flip-flop. The input is given in serial manner and output is taken in parallel manner. And this is another type of representation. In this representation, I am using D flip-flop to construct SIPO register. See here, I am using D flip-flop. Input is in serial fashion or serial manner. So this is red color one is output. From each and every flip-flop, I am taking output parallelly. So this is serial input and parallel output. And clock pulse is given to each and every flip-flop simultaneously. See here, in these type of operations, data is entered serially because serial input and output is parallel, SIPO, and data is loaded bit by bit. If you observe here, I am considering 4 flip-flops because I want to store 4-bit data. See here, I want to store 4-bit data. So that I am taking 4 flip-flops. If you want to store only 3-bit data, 3 flip-flops are enough. If you want to store 5 bits of data, you need 5 flip-flops. The number of flip-flops is equal to the number of bits to be stored. In previous session, I have already discussed this point, and I want to store and I want to shift 4 ones. So this is my data. So here I am taking 4 bits. To store these 4 bits, I am taking 4 flip-flops together. Okay. So data is loaded bit by bit. Okay, next point. All the outputs are disabled initially as long as the data is loading. After that, the data and clock pulses both are very important. So the data input and clock pulse, whenever data is applied and clock pulse is applied, then only it start operating. Okay. So please take care of these 2 points. So number of clock pulses required and the speed of operation. I'll explain these 2 points at the end of slides. Okay. So here, this is my block diagram. Initially, so all the flip-flops are having 0 as output because no clock pulse and no data is provided initially. And I am considering D flip-flop. See here, I am considering D flip-flop to design SIPO register. So some of you may get doubt, why only D flip-flop? Here, I am just loading the data. See here, I am just loading the data and I want to shift the data. So loading and shifting. So loading purpose. Loading means nothing but storing. For storing purpose, we can use D flip-flop. So RS, JK are some different operations. You can consider them. But here, I just want to store same 1111, this number. So I want to store this number. Storing purpose means we have to go for D flip-flop. Once again, please pay attention here. What is the input? My input is, I am considering 4 ones as input. So input is given serially because serial input. So here I want to give my input as 1111. Bit by bit I have to enter my data. And output I have to take here. See here, all these points. So at Q3, Q2, Q1 and Q0. Parallelly I have to take the output. See, 4 ones. I have to get 4 ones. Then only my operation is set to be completed. Please remember this point and I'll show how it is going to be operated. Initially, all the outputs are zeros because no data is given here and no clock pulse is applied. Okay. Now the first clock pulse. So initially, all the outputs are zeros. 0, 0, 0, 0. I have entered here all zeros. And don't consider this one. I'll explain this one. Just please pay attention. 0, 0, 0, 0. Initially all outputs are zeros and I have to enter my data D input bit by bit. First I am going to apply my LSB bit. See, I considered my LSB bit here. I have applied my LSB bit here. Okay. Now see this one. Clock pulse is applied. First clock pulse is applied. Either positive going or negative going, whatever you want. Now for this flip-flop, input is this one. So 0 is input. So D flip-flop produces whatever we are giving as input. 0 is input. So it produces 0. Okay. For this flip-flop, 0 is input. So again it is going to produce 0. For this flip-flop, 0 is input. Again it is going to produce 0. And for this flip-flop, I am giving 1 as input. So it is going to produce 1. So my output is 1, 0, 0, 0. See, this is my output. This is my output. Please pay attention how it is going to be obtained. So this is the output. See here, this is the output after first clock pulse. Now we'll see after second clock pulse. After first clock pulse, my output is 1, 0, 0, 0. See, Q3, Q2, Q1, Q0. My outputs I have entered here. 1, 0, 0, 0. And now I am giving this second one as input. So this bit is already entered in first clock pulse. Now during second clock pulse I am applying this second one. Okay. Now for this flip-flop 0 is input. So output is 0. For this flip-flop 0 is input. So again output is 0. For this flip-flop, see 1 is input. So it is going to produce 1. So 1. For this flip-flop 1 is input. So again it is going to produce 1. So output is 1, 1, 0, 0 after second clock pulse. So after second clock pulse. Okay. Now we will see after third clock pulse. After third clock pulse. So previously what is the output? 1, 1, 0, 0 is output. First of all you need to make a note of this one. After that, so this one is going to be applied here. Okay. Now for this flip-flop, 0 is input. So 0 is output. For this flip-flop, 1 is input. So 1 is output. For this flip-flop, 1 is input. 1 is output. For this flip-flop, 1 is input and 1 is output. So my output is 1, 1, 1, 0. Okay. This is output after third clock pulse. Now see after fourth clock pulse. See previous outputs are 1, 1, 1, 0. So these are outputs. And again these are present outputs. So first of all you need to consider this one. Previous outputs 1, 1, 1, 0 I am giving here. And this last one I am applying here. Please pay attention. So 1, 1, 1, 0 are outputs of third clock pulse. See 1, 1, 1, 0. This one MSB bit I am applying here. For this flip-flop 1 is input. So output is 1. For this flip-flop 1 is input. So output is 1. Again for this flip-flop 1 is input and 1 is output. For this flip-flop 1 is input, 1 is output. So all these, see, all these are outputs after fourth clock pulse. After fourth clock pulse. Now 1, 1, 1, 1. Because I have to take my output parallelly after each and every flip-flop. So for this flip-flop 1, 1, 1, 1. So this is parallel output. My input is this one 1, 1, 1, 1. See, this is my input till now. So during the 4 clock pulses, I have applied 4 ones as input. After 4 clock pulses, I got 4 ones as output. See, this is what I have entered. This is what I got. So both are equal. So data is stored and shifted. So this is serial input and parallel output. Okay. Now, this is the timing diagram of SIPO. In SISO, I have mentioned the same. In this slide, in the next slide, I'll explain the difference between SISO and SIPO. Just listen carefully. Without applying any clock pulse, without applying or before applying any clock pulse and input, our outputs are zeros. After first clock pulse, Q3 becomes first flip-flop output becomes 1. After second clock pulse, similarly third clock pulse, fourth clock pulse. So after fourth clock pulse, all the outputs are ones. So SIPO, this is my input and I have to get my output parallelly across Q3, Q2, Q1, Q0. I got output as 1, 1, 1, 1. This is my input and this is my output. See, input and output. Data is shifted successfully. Data is stored as well as shifted successfully. So, 4 clock pulses are required to store the data as well as to shift the data in SIPO. Now listen, SISO and SIPO. So my input is 1111. After 4 clock pulses, my output is 1111. Serial input, parallel output. It is successful. In SISO, I have mentioned 1111 input. After 4 clock pulses, I got 1111 as output. This is serial input. I have to get the data here. So, what is my output here? 1, but not the remaining. Listen carefully. Serial input. Okay. Serial output. I have to get the data here. 1 is my output, but not the remaining. In parallel output, this is my input and 4 ones mean my output. This is my input and 1111, 4 ones is my output. It is okay. But this is my input, 1 is my output. It is not okay. Means 4 clock pulses are enough to shift the data in SIPO. But 4 clock pulses are not enough to shift the data in SISO. It is enough to store the data. See here, data is stored but not shifted. I will explain. We have to get 4 ones here. How it is going to be obtained? Okay. See, 4 clock pulses are not enough to get 4 ones as output in SISO. But it is enough in SIPO because output is parallel. Here output is serial. Only at this point we have to check our output. This is my input. After 4 clock pulses, I got only 1 but not the remaining. So 4 clock pulses are not required, not enough. 4 clock pulses are not enough here. So we will see how many extra clock pulses are required to get the remaining 3 here. Okay. This is the tabular representation of SIPO. After first clock pulse, what happens to the output? Initially all outputs are zeros. After first clock pulse, 1 is applied to the D3 and 1000 is my output. Okay. After second clock pulse, see after second clock pulse, again 1 is a second, see 1, 1, 1, 1, right? This is my first one. This is my second one. Okay. Is applied and this is my output. So I am designing this table using whatever the operation I have performed in previous slides. During the third clock pulse, this is my input and 1110 is my output. During the fourth clock pulse, this is my input and this is my output. So 4 ones I am applying input and 4 ones I got as output. So serial input and parallel output. Why I am mentioning parallel? So across each and every output. See here, across each and every flip-flop output I am taking the output. So it is known as parallel output. So it is completed. This is the tabular representation of SISO. Here you have seen SIPO. Whatever the data we are giving in serial, we got the same 1111 parallelly across each and every flip-flop output. So it is clear. Now we will see SISO. This is SISO and I have already discussed up to here in last video. So after 4 clock pulses, listen, after 4 clock pulses, this is my data actually, 4 ones as input. After 4 clock pulses, I got 4 ones here. Okay, data is stored in the register, but I am not getting all these data as output because see here, this is my output, this is my input. I am giving 4 ones as input, but I got only 1, but not the remaining 3. Data is stored, but output data is different from stored data. Data is stored and output is 1. I have to get the remaining 3 ones. So to get the remaining 3 ones, again apply clock pulse here. See here, I am applying clock pulse, but I am not giving any data as input. Just leave it, and now it processes the already existed data. It processes already existed data and it results 1, 1, 1. 4 plus 3. Total 7 clock pulses are required. See here, total 7 clock pulses are required to get the data as output. Serial input and serial output. Serially I am entering 1 by 1 as input. I got 1 by 1 as output after 7 clock pulses. But in SIPO, only 4 clock pulses are required because data is entered serially, data is taken parallelly. Here, data is entered serially and taken serially. So, total 7 clock pulses are required. Means SISO is slow when compared to SIPO because it requires total 7 clock pulses. Okay. So, here don't give any input. It processes already existed data and it results the output. Okay. See here, serial input, parallel output. Serial input, serial output. Now, differences between SISO and SIPO I mentioned like this. Required number of clock pulses. Here I am taking 4, right? Number of clock pulses required is equal to number of bits. 4 bits. So, 4 clock pulses are required in SIPO. Okay. In SISO, we require 7, right? We require 7. Number of clock pulses equal to number of bits to be stored plus number of bits to be stored minus 1. N plus N minus 1 means 2N minus 1. 2 into 4. 8 minus 1, 7. Okay. For SISO, 7 clock pulses are required. For SIPO, 4 clock pulses are required. And next difference is time taken. Time taken is also less for SIPO because only 4 clock pulses. N into T, where N is equal to number of bits to be stored. And T is nothing but clock duration. So this one. Either 2 seconds or 3 seconds or 4 seconds, whatever it may be, whatever the clock pulse we have taken, clock duration into number of bits. Here 2N minus 1 into T, again clock duration. This is the difference between SISO and SIPO. Please remember one point. Number of clock pulses is equal to number of bits, means N. In SIPO is fast when compared to SISO. Okay, in next session I will take parallel input, serial output. Okay, thank you.